Okay then, I'll make it past, so I'll kick off because I know that there's a lot of other parallel sessions going on. So what I'm going to try and do today is go through some of the stuff we're doing in terms of developing new architectures and how we're hoping to make them available for people to get their hands on and play with. Particularly two areas I'm looking at, one which is neuromorphic processing and the other is quantum computing. So I'll just give you a brief bit of background on me. My name's Peter Waggett. My PhD is rocket science, which for me is great because if somebody says this isn't rocket science, I can say, well, I can't help you. But having failed to become an astronaut, I looked around for the next most exciting career I could find. And I've either got a limited imagination or there's been something in this IT research that's kept me going for about 20 years. And currently I'm Director of Emerging Technology at IBM's Hersley Labs, which is just outside Winchester. So the first question I usually get asked is, why do you need an emerging technology group? And that's usually by people from business who have done the MBAs and have seen this nice curve about how a product gets out there in the marketplace and how it gets adopted. It's a very smooth curve. You get some kind of visionary comes up with an idea. It's shown to the business people, they adopt it, and then eventually gets replaced by something else. So over time, sales go up, sales go down, something else comes in to replace it. But what happened, I guess, around about the late 80s, there was a guy working in California called Jeff Moore who pointed out actually for a lot of IT and a lot of high technology, there was a gap between effectively the people that understood the technology and the people that understood the business. And what was happening was that a lot of technologies were getting stalled and not really being picked up and adopted. So the aim of the group that I run in Hersley is to play in that chasm. It's to try and act as a bridge between the business people and the technologists and draw them together such that we can get an adoption of technology. And part of it's just due to the fact that people speak a different language. The technologist can't explain the business benefits and the business people don't understand the technology and what it can do for them. So the team that I've got is deliberately multidisciplinary. It's set up so that we can actually bridge that gap. I've got some people who are complete propeller heads who I wouldn't put in front of most clients, and I've got some people that you wouldn't actually realize could code at all. But it seems to work because we've been doing it for about 20 years now. So big part of what we try to do is actually try and also understand what are the trends, what are the things that really are emerging, and how can we try and pull those together. And so we do a lot of work both internally and externally around forecasting. So we're heavily involved in a series of internal forecasts. I mean, the one that people probably have heard of is the Global Technology Outlook. And I'll describe that a bit later on. But that's really our internal forecast that enables us to do a route map for all of the products and the development that we're doing. We've got a thing called the Global Innovation Outlook, which is trying to capture some of the things that happen in society and understand how you can actually take advantage of the fact that society's picking up technologies quicker than a lot of the businesses are doing. 5 in 5 is just 5 technologies that are going to make an impact in the 5-year time frame. And the final one on that is the Grand Challenges, which was the sort of thing that we did where we set the research groups the task of beating Kasparov at chess or playing people with Jeopardy and winning that sort of game. So those are the things that drive our research groups forward. But we're also very aware that we need to be talking to the outside world as well. So I do a lot of work with analysts, with like-minded research groups, academia, and also on client projects. But as I said, the key thing that we've driven a lot of stuff from is what we call this Global Technology Outlook. What happens every year is that the call goes out to the R&D community, gives you bright ideas, gives you thoughts, what's going to be disruptive technology over the next 10 years. Those ideas get taken on board by a committee. That committee produces the report. We then do a gap analysis, and that's what directs where we spend our R&D spend. Every year, the committee gets taken apart and a new committee gets put in place, so it stops it becoming stale, and it becomes quite a competitive thing to try and produce the sort of like best GTO. I may be biased, but the one I was involved in about 3 years ago was the best GTO, but I say I might be biased on that. One thing that's come out of it, though, and one thing that is really becoming quite apparent is that the GTO in the past was almost a case of articulating what's going to happen with Moore's law, in terms of what the impact is going to be. So I've been calling it sort of like automating the world. It's really trying to get things faster and faster in terms of what we've got out there. But over the last few years, what we found is that there's been a trend which is towards actually trying to understand the world. And to do that, what we need is a whole set of technologies that, machine learning, object recognition, video speech analytics, all those sort of things that I've listed up there, that typically are not very well served by a classical von Neumann type of architecture. They get very overloaded very quickly and aren't really able to satisfy some of those requests. So one of the areas they've been looking at is what's happening next in terms of computing. And we've been looking at some of the different things we think and the timescales that we've got on these things here. So what I'm going to try and do is just go through what we think are the sort of like 3 to 10 years out, the quantum computing and the neurosynaptic processing side of things. We paid a huge amount of money for this logo. It's our Smarter Planet logo. So I thought I'd better put it up there. At least we get some money out of return from it. But really all we're trying to say is that we've got a vision that there's a smarter planet out there. It's instrumented, it's interconnected, intelligence driven it, and it's interactive. And I think that interactive thing is the thing that's starting to come out more in terms of we're seeing a blurring of distinction between what's machine generated and what's human generated content. And why do I say that you were struggling with the von Neumann architectures? Well, clearly everybody's familiar with them. They're very simple in concept. I wouldn't like to claim that I could design some of the more revolutionary things that are going on with them now. But you've got an I/O, you've got a CPU, you've got memory, and it's all based around classical ones and zeros in terms of what they do with these things here. And I mean, a summary is that it can check many different possibilities in rapid succession. And the whole industry has been driven about getting that succession quicker, hiring up the clock speeds, trying to understand how we can shorten interconnects to get better transmission speeds through the systems here, but everything in sequence. And that's, I think, where we're struggling. And it's the sort of thing that we need to look at with a different eye on, because regardless of how quickly Moore's law is driving us, it's only stated different ways, but it's only doubling every 18 months. And for some of the applications we're looking at, that really isn't good enough. It is driving the industry in terms of the von Neumann classical systems, but it's really now struggling. And the two areas that it's struggling with are really heat or energy. I mean, how much it's taking to get these things driven at the speeds that they're working at, but also the quantum effects. As we're starting to get smaller and smaller, what we're finding is that we've got quantum tunneling that's causing problems in terms of the error rates and things that are coming through for those sort of systems. So in both of those areas, there are real problems in terms of trying to improve performance quicker than what we're working at now. So the two systems that we've been looking at, the one on the left is what's known as a synaptic chip, and the one on the right is the quantum computer, tackling each of those problems in different ways. So on the left, we're tackling the heat and the energy problem. On the right, we're tackling the quantum, we're in fact embracing the quantum uncertainty and actually using that to process things. So the neurosynaptic chip, I'm probably the oldest one here. So I don't think, did anybody ever remember transputer arrays? Oh, 2. Oh, right. So perhaps I'm not the oldest one. But what they were was a sort of like effectively a small processing element you built up into an array, and every element was interconnected such that you could do processing that's much more similar to the way the brain works. The neat thing about what we've done with the TrueNorth chip is we've actually taken that transputer array and put it onto a chip. So you've got 1 million neurons, effectively, with 256 million interconnections between them. And what that means is that you have to get your head around the fact that you're processing in a completely different way, much more like the way that the brain works. But the energy required for this thing is very small. So running flat out, it's going about 73 milliwatts. Which, given, difficult to give you a sort of like a direct comparison, but, certainly at those sort of levels, you'd be talking about having, say, a mobile phone powered by one of these things that would last for months between recharging. So it's a really quite a revolutionary way in terms of tackling the heat and the energy, but it's doing something very different. Yep. it's getting down to that sort of level. It's becoming a sort of like more of a biological level of energy setup, but it requires a completely different way of trying to tackle these things. But if you think about it, one interesting model is that if you're trying to cross the road, you don't sit there and analyze every single bit around you to understand when it's safe to go across. The time taken for you to do that would probably mean you get run over halfway while you were trying to sort out what the information was coming in. You're looking for changes, and you have, with this sort of system, the ability to pick up changes rather than doing a background search through all the data that's out there. So it's a very different way of working. The quantum computing, again, very different, and we'll go through some of that stuff there. But really, what we're looking at for a certain class of problems like cryptography, drug design, all these different things that require incredibly intricate pattern matching type capabilities, there is a huge promise with a quantum computer to actually do those things very quickly. So starting with the neuromorphic chip, quote on the side is 60% of valuable sensory data has lost its value in milliseconds. If you're trying to think about it, if you're trying to do driverless cars, if you're trying to do things that require interaction with the real world, you have to be working pretty much in real time. If you're not, then you've got very little value coming out of it. Similarly, when we're all looking at, say, information that's on, sensory-like data, you find that it's very difficult to understand what value it is that, if you're picking it up and not doing anything for quite a while. So given this sort of capability built into the chip, the sort of activity you're looking at is the ability to have built-in on-board processing for cameras, cars, phones, all these different things here, such that the actual sensor itself can do the processing and only give out the metadata. So rather than having the issue of trying to gather all the data, send it somewhere to be processed, somebody to do the analytics on it and then do some kind of action on it, actually having this whole feedback loop built into the device itself. And with these sort of capabilities, say particularly the one on the bottom in the center there, this idea of having sort of like a floating drone that can go out there, do temperature measurements and do real-time analytics on it, would enable you to do much better forecasting, but also doing a lot of work around climate change and things like that. And that's really where we're trying to do with these things here. So it's really understanding what benefits we can get from trying to tackle that. To give you an example of the sort of thing that we're doing, this is a famous test that's set up for a lot of the machine learning type of setups. And this one is being collected and processed by this neurosynaptic chip. I'll just run it through first. You can see there that there's some things in there that like the car, which has been flagged up as blue, that are stationary. But we've got this chip tuned such that it can pick up any sort of like cards in there, whether it's moving or whether it's stationary, put them on there. We've trained it on 3 categories of objects. People, which come up in the green, bicycles, which come up in the purple, and cars, which come up in the blue. But interestingly, when you look at this thing through, if I just run it again, we see coming in on the right, there's something which is flickering between purple and green. It's somebody on a skateboard. We never told it what a skateboard is. It's struggling in its real-world construct to actually understand how to classify that thing. So it makes its best guess at the time that it's going as to what it's on there. And what we've been looking at is how we can then start putting learning loops around that, such as anything that comes out as being an uncertainty is reclassified and then put back into the system such that you get a new category and try and work those things through. So that's what we're aiming to do with this setup here. And we've done one system which is, for us, quite parochial in the UK, managing the English Channel. It's one of the busiest waterways in the world. It's got a huge problem in terms of illegal dumping of oil. So a lot of the ships that go around basically clean out their tanks and dump a lot of oil into the English Channel. Similarly, we need to understand what ships are going around there, both from a safety point of view but also security. So there's a sensor that they've been looking at, which is called the Sentinel sensor. It's set up by the European Space Agency, flying at the moment, and it's what's called a synthetic aperture radar. How it works is that it's side-looking. As it flies past something, it gets a huge swath of data and generates that in terabytes of data that then has to process in terms of the system. Traditional systems have to basically wait for the data to be captured. Once that data has been captured, it's processed into an image, then you do image detection on that data. With the Synaptic chip, we've just done a demonstrator which is put up in place of, the idea is that that's going to fly on the next versions of the satellites, such that once the data is collected, it's processed on board, and you only send down the actual points of interest. That enables you to get away from all of this sort of issues of data overload, but also latency in terms of the imagery that's coming through. So that's the sort of application that we're looking at to try and do work with on this Synaptic chip. And the first feasibility studies have been done effectively with offline data to actually prove that if we did have the thing in place, that it would actually be able to get the setup. And the sort of data that we're getting is looking very good. So basically from one of those chips, we're able to pick out and categorize a whole range of different ships and different capabilities of things that we've got on this sort of system. So in that instance, there is no way that you would be able to carry a computer big enough to do that processing on board a satellite. And basically, it would still not be able to process in time to enable you to get this real-time capability. So other things we've been looking at, I'll just play this clip as well.
Hello, Mr. Yakamoto. Welcome back to the Gap. How those assorted tank tops work out for you?
Mr. Yakamoto.
So, anybody know what the film is? Minority Report? We were asked by a retailer to recreate that system for them. And one of the things we needed to do was to get the real-time processing at the level that we needed, because we were using the same way they had their iris recognition. We were able to do that with a Synaptic chip in real time. So effectively, we proved that we could replicate that system using a simple processing algorithm around that new chip. There were several issues with it. I mean, if you see in the film, the two things that happened in the film that don't happen in real life. You don't get the flash of light to tell you you're being looked at, and you can't swap eyeballs. That was the other thing that we found was different from the film. But everything else we could do. And the only issue we had was, and the thing that's slowing us up now, is that the legal departments got involved and basically said, not until you've sorted out all the privacy issues can you go ahead and do this sort of thing. And the other one we're looking at, this one is slightly different in that we're challenged by the BBC to do a system that would allow us to use a gaming headset to drive a London cab around Piccadilly Circus. Again, the legal department got involved, and at that point they said, you can't do Piccadilly Circus. So they let us loose on Santa Pod Raceway. But we built this for a program called Bang Goes the Theory, and basically just thinking enabled you to drive this cab. Now, one of the things we're looking at is it's not an autonomous car as such, because we're actually just driving it remotely, but we're trying to look at using some of these chips and some of these architectures to actually put in safety features. So I'll show you what we did. Okay.
Will our brains be up to the challenge?
Go!
Yes, I've done it! The first ever brain-controlled taxi.
So it was a bit of fun, and by cutting it there, I didn't show the bit where it veered off to the right and took out the barrier, but it's an indication that with these sort of applications that we're trying to look at, we really need to look at a different set of processing capabilities. So the other one I was going to look at this point, I'll give an apology if anybody was coming here expecting equations. I only had a short amount of time, so I decided not to put the equations in. If you want to see about the equations, see me afterwards. Quantum computing, based on quantum mechanics. A couple of things that really drive that. There's a couple of things known as the uncertainty principle. And really what that's saying is that for paired variables, you can't have an absolute knowledge of both of those paired variables. So if you have things like position and speed, or position and velocity, you can't measure both of those absolutely, because the problem is when you try to measure one, you destroy your information about the other one. And the fact that you've got this wave equations and you've got a wave-particle duality, meaning that some things that you expected to act as particles don't do that when you get them smaller. So, for example, if I run into that wall, I can keep running into that wall and I'll just bounce off it because I'm above a certain size where there's not going to be any ability for me to slip through the empty gaps within that wall to get through it. But when you start to get down to the atomic level, what you find is that you can fire, say, electrons at something like that, and every now and then they'll just go straight through. So you've got to worry about all those sort of things as you try and do it. It's a different way of thinking, again, and there's different approaches needed, but it's got huge potential. The promise is that rather than checking things in sequence, we're going to be able to check a huge number of possibilities in parallel. And the reason we're doing that we're based on qubits rather than classical bits. Easiest way I found to sort of like get my head around it is that classical bits have a 1 and a 0. So if you imagine the Earth, what you'd be saying is that with a standard bit, you're measuring the North Pole or the South Pole. With a qubit, you can measure anything around the surface of the Earth and have a different amount of value associated with it. So you can have a different information stored, say, in London as you've got in San Francisco or San Jose or somewhere like that. And you can interrogate those sort of things there. The interesting thing as well is that some of those bits are in multiple states at one time. So the only thing that determines the value is once you do the measurement. And again, part of the quantum mechanical sort of like folklore around this thing is that it's the classic thing as Schrodinger's cat, which is that you don't know whether it's alive or dead until you actually open the box. And you've got those sort of issues coming through on that there. So qubits are incredibly fast, except when you do the measurements. So what you have to be aware of is that there are certain things that classical computers are very good at that qubits are probably going to be slower at. It's only once you start to get into some of the applications that make sense for a qubit do you actually start to get those advantages coming through. So it's theoretically awesome amount of increase in performance. So say, for example, we're all been a lot of worry in the press about crypto decryption and things like that. And by making the RSA keys bigger and bigger, you're actually reaching a point where classical computing can't crack them. Typically, for some of the things we've been looking at, say 1024 key strengths and things like that, you would need probably about 30 qubits to do the processing to decode that in pretty much near real time. So you've got this huge capability coming in, and the key thing is that the performance of a qubit system doubles for every qubit you put onto it. So you don't have to, basically to double the performance, you just put one more qubit. So that means that once you're starting to get your way through these systems, up until say into the 30s, 40s, 50s, you've got more processing power than's been deployed anywhere else in the world at the time. So it's really phenomenal capability coming through. Now that's the theory. The issue you've got is that typically these things are very difficult to set up, and they're very difficult to maintain. The largest numbers of qubits that are really being talked about at the moment is 5. And they are not approaching the theoretical limit of 5 qubits because of errors and uncertainty that come into the systems. And so the simplest calculations that have been done with them are fairly trivial. It's basic multiplication and things like that. So we're starting on a journey with this, but there is a huge potential coming in. So the closer we can get to the theoretical performance and the more qubits we can put into it, then the better we're going to be finding the performance coming through from it. But I say things such as the traveling salesman type problem, crypto decryption, all of those sort of applications are going to be able to be handled in very short order by these sort of systems. One of the things I said was that IBM's been doing these GTOs for quite a while, and just something that has been coming out quite consistently is that we need to look at quantum computing. So last month we launched what was our quantum program, which is going to try and get things going in terms of the quantum experience and get people in the developer community involved in this sort of activity. So March the 6th, we launched this program. It's effectively now an open program where, and I'll give you the website where you can go into, where you can sign up and you can start to get access to one of these systems. You're able to go in, play with a 5-qubit system, and play with simulators around those sort of systems, such that you can understand how to put together your processing around a quantum computer. The intention and where we're working towards is clearly to start producing these things in tens of qubits. But I think what's been really important, and this is quite an interesting demonstration of what we're trying to do, is that we're embracing the fact that we know at the moment the qubit systems that we've got in place now are not perfect. They do have errors coming in. The ideal qubit system would be completely isolated from any interactions with the outside world, i.e. any vibration or anything that comes into it would be a problem, because that will affect the capabilities of the systems and it will introduce errors. So one of the things we've been looking at is how we can actually approach a more perfect qubit, i.e. lower error rates, but at the same time increase the number of qubits that we're putting together to actually do this sort of processing. So there's a concept that we put in place which we're calling the quantum volume, which is basically an indication of just how close we're getting to the theoretical capability of individual qubits, and then understanding how many qubits we can actually key together. Because one of the things that I think is apparent and shown up quite high on this thing here is that you've got a high error rate on these qubits. Actually increasing them doesn't help you, because your errors are counterbalancing the increase in performance you're getting from the individual additional qubits. So we're going to make a push to try and get the error rates down, and then start to look at putting more capability around them. And they say the call for the developer community, I think, has been really quite interesting, because this is a big unknown. We don't know, we can't understand at the moment. Clearly, the easy problems for classical computing, frankly, it's not worth us using a quantum computer for. The hard problems it is, and there's also some that we're able to look at that we don't even think we've been able to address in terms of the classical architectures and putting things in place. So for us, I think this is going to be a fairly big step, and it's certainly something that I think we're going to be seeing a lot of work on. But we do realize, and one of the things we're looking at is just how we actually get this developer community getting in place and trying to understand this thing. So the one website that I've got on here, which is, I say, is worth looking at, is the one I've listed down the bottom. So it's IBM Research, research.ibm.com/IBM-Q-QX, and that's Quantum Experience. But there's a whole set of things in there. So there's tutorials, there's simulations, there's graphical programming. SDK will be coming soon for the APIs, and access to a fully operational 5-qubit system over the web. So people can come in and actually run stuff on that. To date, in terms of launching the thing, we've had 40,000 users, 275,000 programs have been run on the thing. There's been 15 scientific publications gone already, which, given that we've been in a sort of like an alpha and beta and now launch state, is pretty good. and we've got 10 departments looking to use this as part of their teaching program. So that, I think, is the important takeaway. Is probably that website. If you're interested in this sort of area, is log on to that. It gives you an understanding of what the quantum computing is around. It gives you an understanding of what the capabilities are, but it also gives you access into this system that we put in place. Now, so one thing I've always been aware of is, in fact, going back to one of the classical articles that were written by Niels Bohr, who was one of the founders of quantum physics. And he said that prediction is difficult, especially about the future. So what I'm giving you is a lot of predictions. Take them with a pinch of salt. But if you're not convinced by anything I've said, I've got this nice graphic here, which is the classical computers in the 1940s and the quantum computers of the 2010s. I think there's pretty good similarity there. So 60, 70 years, then we should be reaching the point where quantum computing takes over completely. So I'll stop at that point and open up if there are any questions or any comments.
Yeah.
Yep. Oh, sorry.
Okay, all right. So can you give us an idea of what type of problems, are more appropriate for quantum computing?
Yeah. So the problems you get, I say, is that until you actually measure something, the quantum computer is very fast. So what you don't want to do is do your standard problems that require a huge amount of measurements. So it's not going to do things like make video stream quicker or media streams quicker. It's not going to do anything like do more intricate calculations unless you factor them up correctly. But say for 1024 crypto decryption, you're talking about 30 qubits to do it in a matter of minutes. Whereas if you looked at a classical architecture, then you're talking about a gigahertz processor would probably be about 3,000 years or something. I think was the number I saw on that one there. So anything that scales at a level such that it becomes difficult to understand how you could get it there is the sort of thing we try and do. Scheduling problems, scheduling again is one of those things that becomes very complex very quickly, and again that's the sort of thing that would be very appropriate to try and do it. Image matching, pattern matching, anything like that that's got a form that you're looking at rather than a series of measurements that you're making. Those are the sort of things that it will be best used for. But I say, unless you're going to get something like about 30 odd qubits working efficiently, that's once the thing starts to become a real practical proposition.
Can I ask one more?
Yeah.
And is there going to, are you envisioning some sort of hybrid architecture where you have like the traditional?
Yep. Yeah, so the idea is that, I guess going back to and again, this is not a direction, it's a thought more than anything else, is that typically I've deployed things like FPGAs and different things like that. It's sort of like they've been hosted on a system that handles all of the stuff that the system's not particularly good at, and it just has that as a if you like, a plug-in effect. We try and do it. Now, given the constraints around quantum computing at the moment, which is that to minimize the vibrations and to minimize the errors, you have the thing very cold and things like that. It's probably going to be something you're going to be able to throw stuff across the web. But I think then that's the architecture they're looking at with this developer community. So, say for example, on the crypto thing, you'd have the ability to package up the thing you're trying to decrypt, fire at the system, the answer would come back, and then you would carry on doing the rest of the processing around the edge. So I think that's probably a good model to think about how it would work out. I don't think you'll have standalone ones, certainly for quite a while.
Thank you.
Sorry.
Yeah, thanks for IBM opening up this, fantastic technology. Yeah, I will set up, right away. Yeah. But what can we learn and solve some, real-world problem with this quantum, computer IBM open up? Yeah.
Well, it's the same sort of thing that we're looking at there. I mean, anything that requires, say, scheduling programs, any kind of drug discovery type of things where you're trying to pick up patterns in data and patterns in structures. All of those things would be very appropriate for a quantum computer. It's really those sort of complex tasks for traditional computers that are the things we can try and throw this thing out.
Searching from a complex video,
Yeah,
searching
yeah.
pattern, right?
Yeah.
Okay. The second question and follow,
Yep.
is important because Chinese government, China actually,
Mhm.
they claim that they have invented kind of a quantum network, and
Right.
they even launched the quantum satellite into the space. And they say they have already developed quantum communication. They have no way, to try to attack, and it's very safe. It's kind of very sophisticated, isolated,
Yeah.
advanced communication system. Yeah. So I wonder what you think about China's claim and how.
I think this is the sort of thing that there'll be several groups working. I know there's some very strong groups around particular countries. So Australia's got a very strong group to work in this space. There's some in the UK, some in Switzerland. I think at the academic level, my hope would be is that it'll be the standard academic model that they'll publish and share, and that way will drive the knowledge forward. So there's no monopoly on good ideas and good thoughts. I think everything we do to pool that knowledge, I think, would be worthwhile.
Okay, great.
One of the things that kind of Bob has mentioned for us is the power usage. You talked about 50 node, 50 qubit systems.
Yep.
Have you done any calculations around what the kind of power usage might be?
It depends on the particular architecture you're using for your qubits. Some of them are set up with MRI type imaging systems that are being used to actually do the positioning, but also do the measuring of the systems that are on there. So, MRIs are fairly intensive users of, energy and also helium, which is another major issue you've got. It's a different way, a different problem, because a lot of it is to do with the cooling and everything else you need to do. Most data centers will run at ambient conditions, whereas these things are going to work at effectively close to zero. So, short answer is no. In terms of the practicalities of it haven't done. But on the counterbalance, if we're talking about 30 qubits, it is only 30 bits. So whereas we're seeing the stuff that's put in place now, which 20,000 cores or something like that, for something that's putting it out there. Instinctively, if that can be replaced by a much smaller number of qubits, then you would think that there would be some kind of benefits coming off it. But we're not at the stage of actually planning these things out yet. Yep.
So it sounds like controlling for errors is one of the difficult challenges.
Yes.
What are the standard techniques or what techniques are you deploying?
Well, I think this is possibly one of the more exciting areas. And the reason I'm saying that is that I think we're moving, with these sort of systems, and actually even with the neuromorphic systems, you're moving into a more probabilistic-based domain, where I think we'll be trying to develop programming that accepts a degree of error. And so, you really, what you're looking for is detecting the catastrophic problems that mean you've got, you really have got an issue and got to go back with it. But I think we're going to be getting answers that are going to be more, the answer is probably this, rather than it's definitely that or whatever. So I think that there is a sort of like a theory that you might actually end up having a more probabilistic programming model that comes into these things. But if you go with these things here, the actual you can minimize the errors by minimizing the advantages you get out of the qubits, and that's what's behind this idea about the quantum volume. If, say, for example, you took the model of the Earth and you gridded it up into 10-kilometer grids, and you had an error that was a couple of kilometers, then that may not be too big a problem in that it'll, effectively net out to be at the same point that you're trying to work the data from. But if you had a, 10, 100 meter error, then the whole thing would be impossible to use. So you might have to go to, say, a 1 kilometer grid. So that there are different approaches that you can try and do these things. I think it's safe to say that nobody's got the real answer yet. So, it's an interesting area to look into.
But the approach seems to be more on tolerating errors in software programming as opposed to
Yeah.
working more on
Well,
level.
yeah, because the problem you've got with some of these things is that, say you have to quantum mechanically isolate the whole system from everything else in there. Vibration and the level you're talking about an atom being affected by vibration occasionally will be a problem. So I think we'll have to have more tolerant and more correction built into the software than the actual hardware elements of the system. Yeah?
I guess I'm betraying my limited knowledge of quantum computing here. From what I understand, it's like I've seen it described before where you start thinking of molecules and that you actually put that in the superposition, and in a sense you put the structure of the molecule similar to what you might do with like logic gates or something. I was wondering, is that what's going on too?
Yeah, I mean, basically, what you're trying to do is that you are applying energy to a system to put an element of it out of kilter, such that you've got the capability of getting a reading back on that one that then enables you to do it. So, you're having to manipulate at the atomic level, certainly to try and get some kind of capabilities on there, and that's compared to. But then the problem we've got with a lot of the hardware development at the moment is that we're getting down to levels in terms of the gates that we're trying to construct with the material substrates that are reaching those sort of like atomic levels, such that the quantum effects mean that electrons can tunnel through and things like that and cause problems. So we're going to hit those problems anyway, even if we just stick with the classical architectures, I think. There's one over there.
Yeah, I mean, so Jill North was talking about China and quantum entanglement was.
Yep.
Understanding is what their experiment was about, and I guess when I was thinking about that, whenever they saw the article in IEEE on that same topic, it's like it seems like in that case it could be like serial communication. You're thinking USB, you think
Mhm.
single, spin, and so if you can detect something in a serial manner, you only have a smaller subset to isolate, I guess, right? So in other words, fast communication to, like in this case, a cluster somewhere else to do the processing.
Yeah.
Then you could onboard with fast, near real-time communication, having the processing offset somewhere else, but also the feedback would also be near instantaneous, even if it were, essentially a serial cable over the air.
I mean, I think
All
there's
kinds of crazy implications. To
I think there's huge promise. I think it's going to be a case of understanding how we can realize this rather than claiming up front that we would know all the applications and ways that we could put this stuff together.
Or even like multicast. Or,
Yeah.
a group of quantum entangled.
Yeah.
That'd be really interesting.
I say I think there's huge promise, and I say certainly I think that it'd be good to sort of like get if you're interested, get into that website and see what you can pick up from it.
Have anything on the neuromorphic chips like a site to look at?
That one's a bit more interesting. There is if you go to the main IBM site, you can pick that thing up. We don't have the capability to have simulators or have that thing set up. There's limited production run at the moment. There's only 100 in the world. We've got 3 of them, and the rest of them being handed out to academics. It's not at this stage a fully productized version, but it's just a different architecture that we think has got some real promise. But certainly the quantum one has been opened up, so that one is able to get into.
I just want to follow up about that because you would probably describe the satellite imagery as a lot of agencies, 3 letters and 4 letters like NASA that have those problems, and they even.
I can imagine they are, but if they were, I couldn't tell you. But no, I mean, the group that we're working with is the European Space Agency, and that's all on purely civil applications of the imaging side of things. But the capability could be used in a number of different ways. Yep.
What would you say the rate limiting step is for this? If you had unlimited resources, would you be able to tackle this problem quicker?
I think it's more it's the bandwidth on the academics. Now, if you put more money in, then they'll flock to it. But it takes a long time to get your head around and get the thought around this thing here. I think there are a few departments that are very strong, but I think there's a lot of I think that's going to be the limit. It's going to be the academics and the people working in the space rather than at this stage the money necessarily.
Does it scale with what we're talking about, the actual physical scale and the tools to actually be able to measure the things? Is that also a huge limiting factor?
Well,
aside from just being able to try to study?
no, I mean what they're looking at is effectively single atoms. So in some systems have been using say the Australians I think are using silicon a lot as their substrate, but others are using particular atoms where you're picking up effectively you're manipulating the spin on the outer electron and things like that. So and you're doing that usually with something like MRI type systems and a atomic probe that will try and direct them. So it's heavyweight systems in terms of the designs they've put in place for them.
I was reading Mitchell a physicist of the future, and he was talking about a mouse MRI. Look at mouse MRI.
Yeah.
MRIs of an actual mouse, but there was a guy who was working on trying to shrink down an MRI to where it didn't have to have a uniform field.
Okay.
I don't know if that would have any implications for.
It could do. I mean, it's like one of those things that my background, so part of it was radio astronomy, and we used to keep building bigger and bigger dishes, but then everybody found that single dipoles dotted across the field and clever maths could enable you to synthesize an array that was bigger than the biggest dish that you could put out there. So I think that again that's an interesting area, is that you could almost have an interferometric type approach to some of these things, and that again might be an interesting way of doing it and cut down some of the costs and capabilities on the systems.
I think another interesting aspect of it, some of the technologies that will have to drive that, such as the possibilities of that, could also then fold into healthcare aspects as well, to be able to have a whole lot of early detection. Early detection. So in the case of the technology, right, to manipulate the spin.
Yeah.
We're also in MRI technology, and then that gets better.
Yep.
It's possible that every doctor could give you a full MRI with some smaller device.
Yeah.
Multiple times a year.
That's right, but I do think there've been some issues. I think lack of helium is going to be a problem at some point, because it's really being exercised by the existing MRI machines we've got out there, and I think that there's a definite shortage of helium, which it just seems a bizarre thing to have to worry about. But yeah,
I would like to know what real objective or purpose for IBM to open up this, resource.
it's to get a community of developers out there that are able and willing to pick this stuff up and work with it. So again, it's down to the skills and education and putting the thing in place.
I see.
Okay. Thanks very much.
Very good.